Okay, today we're going to look at projectiles that are launched at an angle. So now we're looking at a full parabola where the object is launched at some velocity v and at some angle. And if we walk through some of the basic concepts here, we know that at the very top of the path, right here, the velocity in the y direction is instantaneously at 0. The horizontal speed at any point, the vx, at any point remains the same because we're not going to have any acceleration in the x direction. So vx is a constant. So the velocity in the y, however, is going to change due to gravity. And just like when we did the horizontal motion, we'll analyze the motion completely independently. We just have to add two steps. First, we're going to need to find the components of the velocity in both the x and the y direction. And then second, we'll deal with the time factor. But let's first take a look at what general procedures we'll use to solve this. Okay, so just like before, make a quick sketch of the scenario. 2, make a list of the unknown information in both the x and the y directions and chart to separate the motions. Typically, we want to solve for time because the position of an object is based on the time or horizontal position of that object. So oftentimes, if we can find time, we can find everything else that we need to know. We're going to use that time, step 4, to determine the unknown value that you're looking for. For instance, how high is it or how far away horizontally is it? So let's walk through an example. Let's take a look at an example that's launched at 10 meters per second at an angle with a horizontal of 30 degrees. So all we are really given is that we have this object that, I don't know, makes a shape like that. It's a parabola. This angle is 30 degrees, and this initial velocity is 10 meters per second. So we want to find the components of the velocity. So A, we're looking at what are the components of that velocity. So it's 10 meters per second at 30 degrees. So we want to know the Vy and the Vx. So we can find the x as the adjacent side. So adjacent to hypotenuse is the cosine. So the velocity in the x is going to be 10 times the cosine of 30. Which, if we do that, cosine of 30 is 0.866. So the cosine is 0.866 meters per second. The velocity in the y is now the opposite in hypotenuse. So opposite hypotenuse is the sine function. So that's going to be 10 times the sine of 30. And that comes out to 5 meters per second. So that would be the answers to part A. And now we're going to use those values to continue along our path to find the other information. So part B is asking for, well, how long is the object in the air? So now let's take and go over to our chart. And this is going to help us find just about everything else we need. So the velocity in the x stays constant at 8.66 meters per second. Come on, there we go. And now the velocity here, we can do a couple of different ways. But if we take it from and look at this projectile, almost as a horizontal projectile, we can look at this right half, and if we look at that, we have a velocity in the x of 8.66, because that doesn't change. When it lands, it will land with the same velocity that it left the ground with, so the y component of the speed is 5 meters per second, and the horizontal component doesn't change, 8.66. So if we deal with looking at this right half of the parabola, we can solve it just like a horizontal projectile. The only difference is that to find this total distance that the object travels, we'd have to double that time because this is half of the parabola. So I'm going to say the velocity at the top of the path instantaneously is 0. The velocity at the bottom in the y direction is a minus 5 meters per second. gravity, I'm going to use as 10 meters per second downwards, so it's 10 meters per second, or per second squared. So here, again, from our procedure, if we can find the time, we can solve a lot of other things. So the time to go from the very top down to the bottom, we can use our acceleration equation as velocity of the bottom minus velocity at the top divided by gravity. So from there, we have a minus 5 minus 0 divided by a minus 10, so the time is 1/2 of a second. Now, this time, we can now move, just as we did in the horizontal projectile, over to the x column, except now our time, for the total time in the air, we have to double it, because now we have to account for this half, because this we said was t is equal to 1/2 a second. This is t is equal to 1/2 a second. So our total time is then twice that 1/2 of a second, which is 1 second. So that's the total time in the air. So that would answer part B. So its maximum range then is d is equal to tv. So the total time in the air is 1 second. And the velocity horizontally is the 8.66. So that becomes 8.66 meters. So that would be our total horizontal distance in the x direction. So this would be the answer to part C. Part D, we're looking for maximum height. Well, maximum height happens here at 1/2 of a second. So we can come back over and look at our linear motion equation, d is equal to vit plus 1/2 at squared. Now we can use the full equation or recognize that at the very top of the path, this vi is 0, the top of the path is 0, and find that maximum height then is 1/2 the acceleration of 10 meters per second squared times the time of 1/2 of a second, and we get an answer of 5 times 0.5 squared, which is 1.25 meters. So that would be its maximum height. And that would take care of all the parts of the question. So to recap, step 1, find your components of motion. Set up your table with your known information. Solve for your time as we had before. Remember to double your time for the x motion to find out that total distance, maximum distance it travels horizontally. And then do d equals tv to find that maximum range. Okay, let's take a look at another one. Pause this if you need to get your notes, but try to rework this separately on your own. Let's take a look at another one. This one's a little bit more tricky, where here we're going to throw a stone, but we're not going to be at maximum height, but we're going to land somewhere in between maximum height and the ground. So let's walk through what we have. So here we have a stone with a message attached thrown toward an open window. If the stone is thrown at a distance of 6 meters from the base of the building, at 60 degrees with the horizontal, at a speed of 10 meters per second, we want to know what height does the stone enter the window. So here we have some sort of a projectile, and here's our building. And in here we have some open window. So we want to know what is this height here, this dy. Well, we're launching this at an angle of 60 degrees at 10 meters per second. And we are standing away from the building at a distance of 6 meters. So now we're just concerned with what is this dy. Again, whenever we have this angle, set up our components. So Vx, Vy, so we have the horizontal component is 10 meters per second times the cosine of 60. And the y component is 10 meters per second times the sine of 60. And if we calculate those, 10 times the 60 cosine gives us 5 meters per second in the x, and in the y we'd have 8.66 meters per second. So then go over to our table to separate our information in the x and y directions. So here we have the velocity of 5 meters per second. We're standing at a distance of 6 meters away from the building. We know that in the y, gravity acts as a minus 10 meters per second squared. And that the initial speed, because now we're taking the speed not from the maximum height but from the ground, vertically it's going a positive 8.66 meters per second. So ultimately we want to find this height, how high, and in order to do that we need to find the time. Well, I don't have enough information in the y direction, so I come over to my x. So t is equal to distance divided by velocity, which is 6 meters divided by 5 meters per second. So the time it takes to get to the building is 6 divided by 5, which is 1.2 seconds. So t now I can put over here is 1.2 seconds. Well, now I have all the information that I need. From this, I do not have VF, so I'm going to use the equation that t is equal to VIT plus the 1/2 AT squared. So this gives the height of the projectile at any position, knowing the initial vertical velocity and the time in the air and the acceleration due to gravity. So I'm going to start here with my positive 8.66 times my time of 1.2 seconds plus 1/2 of a negative 10 meters per second squared times my time of 1.2 squared. So now when I put that in, times 1.2, so this gives me 10.39 plus 0.5 times 10 times 1.2 squared is a negative 7.2. So 10.39 minus the 7.2 gives me a height of 3.9 meters above the ground. So that is the height that it enters the window. So recognize that we've used the same procedure as we did before. The only difference here is that we did not double the time because we were interested in the height at this particular time.